I will not admit the records. This is the last. Fatima, where are you so many times? Where are you? So, on the last lectures, we discussed, if you remember, the one way of the blood circulation, and we discussed that the intensity of the flow is determined by the factor related with the intensity, G. This is a Poiseuille formula. Do you remember?
Yeah.
No, I don't know, but you have to note, if before you have slight marks, now I will write marks very strikingly. And the attendance, they are 67, the half of the attendance they have to be. Now I will discuss the blood circulation, and you have to pass me all this material for the next week. As you see, I repeat, this is the Poiseuille formula, and intensity of the flow can be divided, a parameter which determines the intensity of the flow can be divided on the two segments. They are the delta P, the differences of the pressure between, I will not respond, make the response, between the beginning and end of the tube, and also the complex parameter, which includes the R in the 4 power 8 L eta, and which is known as a resistance. As you see, this parameter depends as on the parameters determining the vessel's geometrical characteristics, like the L, length of the vessel, and R, the radius of the vessel, and also eta, the physical characteristic of the blood, its viscosity. This resistance is parameter R is known as the resistance of the blood circulatory system. This shows both as a pressure generated by heart, or in this case we can say that it is the energetical characteristics of the heart, also the property of the blood circulatory system, including the blood vessels and blood, determined the intensity of the blood flow, which is very important for the normal functioning of the whole body, normal functioning of the different systems and organs. That's why now we will discuss the resistance of the blood circulatory system. As you can see, it can be divided on the series of blocks, which we will discuss now. They are the physical characteristics of the blood. I will not ask you. If will be something unclear, you can ask me. No problem for me. You have to study everything that I explained now. Is this clear? I will not ask you.
Yeah.
So there are physical characteristics of the blood, the viscosity of the blood, protein content in the blood, in plasma, blood cell concentration in the blood, also type of the blood flow, laminar or turbulent. There are also extravascular and endovascular mechanical forces. There are vessel form, length, and diameter, and the properties of the vessel wall. We will discuss now the first. What about the blood viscosity? No, you had made the viscosity. It is laboratory work. It is the characteristic of the moving liquid, yes, moving, and blood viscosity is that as the blood is a complex non-Newtonian liquid, the blood viscosity depends as on the plasma viscosity, also on the number of the blood cells in the blood. Blood viscosity is determined, blood plasma viscosity determines on the proteins content in the blood. Proteins, there are different proteins in the blood plasma. Why you have to come so late? There are different proteins in the blood plasma. It was shown that the protein albumin, which amount is most high in the blood plasma, it is not affected importantly on the blood viscosity because it is a globular non-active anisotropic protein. The fibrinogen, due to its high anisotropic property, high density and lack of the charge, it is neutral, maximally influences blood viscosity index. Increase of the fibrinogen content in the blood supports the increase of the erythrocytes aggregation, causes deceleration of the blood flow, stasis, and leukocytes migration at vessels wall. Hence, danger of inflammatory damage of the endothelium is increased. High content fibrinogen. What?
Fibrinogenesis protein used for clotting, correct?
What protein?
Fibrinogen, I'm asking.
It is blood plasma protein, which is anisotropic and very actively participates in the regulation blood viscosity. With increase of the fibrinogen content, blood viscosity will be importantly increased. The albumin, no, as I know, have no impact on the regulation of the blood viscosity. The globins like the immunoglobulin M, J, they have different impact. As you see from this picture, the immunoglobulin M has important impact on the blood viscosity, where immunoglobulin G, no. No, this is related with their structures. And they are also important the temperature factor in the regulation of the blood viscosity. When you made a laboratory work, you had possibility to see that with the changing of the temperature, the aggregative properties of the viscosity of the different liquid changed, as the blood plasma contains the different proteins. Among them, there are the specific proteins, the thermogenins, which aggregative space, aggregative property will be changed in the very narrow interval of the temperature, the physiological interval from 35 to 40 grados. And in this interval, when the body temperature increases, it is clear that the proteins will be transformed in the liquid state. The blood viscosity will be decreased. So flow intensity will be increased, and in this case, it will be developed the venostasis, not equivalent filling by the blood, the atrium and ventricle, which will induce the disorders in the heart rhythm. That's why patients usually when they have a high temperature have the disorder in the heart rhythm.
Can you repeat about the artery?
What?
Can you repeat what you said about blood flow in the artery when a patient is
when they have a high temperature due to the decrease or the protein transforming into the liquid state, blood viscosity will be decreased, the flow in the veins will be increased, which will be induce the vein stasis, not equivalent distribution of the blood between the atrium and ventricle, which will be related with the disorder of the heart rhythm. That's why in patients with a high temperature, the heart rhythm is disordered. There are also proteins which can transform from the liquid into the solid state in the very small interval of the temperature, physiological interval, and this is related with the in the cold conditions, the surface capillaries in the surface capillaries in our fingers, the who has the very surface placement of the capillaries, their blood in these capillaries will be decrease their temperature, and viscosity due to the solidation of the proteins will be increased. That will be related with the disorder of the oxygen supply to the fingers and pain in the fingers. It is known that at 0 degrees Celsius, blood viscosity threefold increased than norm. This factor, along with other factor, determines blood circulation decrease in cold conditions, and sometimes it is a cause of the finger pain in humans. This about the blood plasma. Now we have to discuss the blood cell number. The volume of the blood cells to the volume of the whole blood is known as a hematocrit. You can see this is the volume of the blood cells. This is the volume of the whole blood. Normally the hematocrit is about 40%. The increase or decrease of the hematocrit has a very important impact on the blood viscosity. But for example, when the patient has a severe anemia, blood viscosity will be importantly decreased, maybe twice decreased. This causes decrease in the resistance of the peripheral vessel towards the blood flow, intensification of the venous flow, disorder in the cardiac output, and also like in the increased temperature includes the disorder of the rhythm of the heart. The increase of the hematocrit during the polycythemia has also important impact on the blood viscosity, as the largest cells are erythrocytes. That's why most important impact on the regulation of the blood viscosity has the erythrocytes count. Polycythemia conditions, the blood viscosity will be increased, which will be support the decrease of the intensity of the flow and may induce the development of the hypoxic conditions in the body. This is important to be taken in the account when they have to make the erythrocytes mass transfusion. It must be not too high amount of the erythrocyte mass, because when the hematocrit will be above 30%, it will be very importantly increase the blood viscosity and cause decrease in flow intensity and oxygen transportation. They are also known the different genetical anomalies of the hemoglobin, which can induce the changing of the hematocrit. In this case, we have to discuss we know that the hemoglobin chains, there are 2 alpha and 2 beta chains, and they known the genetical mutation when the alpha and beta chains have a lack of the amino acids. In this case, the hemoglobin will become small, light, and erythrocyte also will be small, light. And in this case, this is known as the thalassemia, lack of the globin chains. When we have a small, light hemoglobin, the erythrocyte will be decreased in volume, hematocrit will be decreased, blood viscosity will be decreased, and the effect will be the same as in the case of the anemia or in the case of the high temperature. Now let's discuss the erythrocytes. As you know, the erythrocytes are the double concave disc, and this form gives its possibility to increase its volume, surface area, and support the intensification of the gas exchange. But the diameter of the erythrocyte sometimes is more as the diameter of the very small blood vessels, capillaries. That's why the non-changing form of erythrocytes will be not give its possibility to move across the capillaries. In this case, we have to know that the erythrocyte may be characterized by the very high deformability. The erythrocyte's deformability is related with the properties of the erythrocyte's membrane, its high fluidity, and also a property of the erythrocytes itself, because they have no mitochondria, internal organelles. Their internal environment is very fluid. That's why erythrocytes can very easily change form, you can see like here, and move in the narrow capillaries. In this case, it is very important the different structural property of the membrane, and during the mutation of the skeletal membrane proteins, when they lose the ability to change form, it is possible the here genetical disorder and hereditary sporulation, when the spheric erythrocyte can change form, and due to the mutation of the spectrin, and have no cannot move in the narrow capillaries. They are also known the genetical mutation of the hemoglobin, replacement of the glutamate by the polar valine in the initial structure of the beta chain. As a result, hydrophobic valine penetrates into the second beta chain area of the deoxyhemoglobin, causing aggregation of the hemoglobin molecules and formation of rod-like spiral S fibers during the sickle cell anemia. Oxygen saturation desaturated, crystallized hemoglobin, decrease in ability in erythrocyte deformability, and thus increases the blood viscosity. In these cases, the erythrocyte will be packet one and produce the stasis. The very important impact on the regulation of the blood viscosity has also the velocity of the motion of the erythrocytes. They are known as the higher is the velocity of the motion of the body, the higher will be the friction forces influence on them, and on it, and higher will be its deformability. Therefore, when the rate of the blood circulation is low, erythrocyte will be not enough deformed, which will be support the stasis of the erythrocyte and disorder of the microcirculation. When the speed of the motion of the blood flow increases, erythrocyte will be packed one after each other, and rheology will be improved. So as you see, erythrocytes deformability is the main problem of the microcirculation rheology. No, it must be noted that in macro vessels, the erythrocytes will be not distributed in the micro vessels. Their form is not important for the distribution of in the macro vessels because they are wide, but according to the thermodynamics law, as all processes are directed to the decrease of the free energy, increase entropy, all cells will be directed to the center of the vessels, and in this case, the erythrocytes will be distributed in the center and small cells on the side. So this is known as a Faraos-Linwick's effect. Now we have to discuss the laminar and turbulent flow. If you remember on the last lecture, we discussed that the laminar flow is a flow where flows are moving parallel to each other, no mixed, and where will be the maximal speed of the flow?
In the middle.
The center.
In the
At the
center.
center.
Okay. But the turbulent where they are mixed. The turbulent and laminar flow can be characterized by the Reynolds number. R is equal to rho VR by eta, where rho is the density of the blood, V is the speed of motion of the blood, R is the radius of the vessel, and eta is the viscosity of the vessel. In this case, you have to know this formula, and you have to also take in attention that when the Reynolds number is more as 300, the flow may be turbulent. When it is less as 2,000, it will be laminar. So from this, it is clear that the type of the flow is determined by the type of the properties of the liquid. So its density, its viscosity, also on the speed of the liquid motion and radius of the vessel. Now we discussed on the previous lecture that when the speed of the flow increases, when the speed of the flow increases, what will be matter? Laminar flow may be transformed into the turbulent, yes?
Yes.
At the same time, when the radius decreased, according to the equation of the stationarity, speed has to be increased in the proportionally to the square of the radius, and increase of the speed will support also development of the turbulent flow. What kind of flow we have in the blood vessels? In the blood vessels, usually the flow is laminar in straight vessels, and it is turbulent in the banded and bifurcated vessels. No, in laminar flow is in the arterioles, flow is laminar. In the aorta, where is the maximal speed of the flow? Where is the maximal speed of the flow? No, in the beginning of the vessel,
Yeah,
yes? Or
beginning,
in the
yes.
aorta. In the aorta, yes?
Yes.
In the aorta, due to the highest speed of the flow will be what kind? Turbulent.
High speed.
And the,
Turbulent.
huh? Yeah, what?
No, I was just saying, okay.
It will be turbulent. And the sounds we can hear during the by the stethoscope, it is related with the sounds of the blood excluded from the ventricle into the aorta, or the turbulent flow of the aorta. No, we use the property of the turbulent flow for the measuring of the pressure. You know that in this case we have to press the blood vessel after it will be closed, after we have the continuously decrease the pressure. With the decrease the pressure, first there will be developed the narrow thin flux of the blood, it will be turbulent, and the first found sounds detected by the stethoscope will be the and sounds will be the systolic and diastolic pressure related with the known as the Karatkov sounds. So as you see, the turbulent sounds are usually used to the detection of the pressure. Next, we have to remember the equation of the stationarity. Do you remember this? What is it, the equation? SV is constant.
Constant.
Yes, and so what means as wider is the vessel,
Velocity
velocity
decreases.
of the decreases. Now, what about the aorta? Its cross-section area is 2.5 centimeter in square. Each arteries, arterioles, capillaries by each are narrow, but as they will be divided, the total cross-section in the capillary network, you can see, is 1,000 times fold more as the cross-section of the aorta. So where the speed of the blood will be more, in aorta or in the capillary network?
Aorta. Aorta.
Speed will be more.
Lower cross-sectional
And
area
where
of the
it will
aorta.
be, and where it will be less?
In the capillaries with the larger cross-sectional area.
Yes, 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 you can see this. And right, due to the low speed in the capillary network, it is the time for the diffusion and exchange of the gases in nutrients in the capillary network. Okay. Now you can see here that the pressure, where is the maximal pressure? Where is the maximal pressure?
In the capillary.
Where is the maximal? In the artery. Where is minimal pressure?
In the capillaries.
Capillary.
No, no, no. Pressure, no.
The veins.
Pressure is, here you can see, in the veins, of course. Speed is minimal in the capillary, but pressure is minimal in the veins. Yes? Yes?
Yes.
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 Yes. No, you can see here where there is the atherosclerotic plaque, the speed will be increased, but the pressure will be, according to the Bernoulli equation, decreased. What kind of flow will be in place of the atherosclerotic plaque? As the radius decreases, it will become what kind? Turbulent. Turbulent. Yes. Yes. Now, when the blood is excluded from the ventricle into the aorta, it is excluded from the wide area in the narrow aorta. And in this case, also, it is one of the causes that the flow will change its spectrum and became turbulent. But after you can see, after in the tube, after some distance, there will be developed the laminar flow. In this case, according to in the relation of the aorta is very short. That's why it will be not develop the laminar flow in the aorta. And the third is that the aorta is bended. You can see here is the laminar flow, which is distributed according to the classical distribution, the speed in this maximal in the center of the tube. When the tube is bended or bifurcated, you can see that the distribution of the speed in the place of the bifurcation or bending will be changed. Or this means that the flow will become what kind? Turbulent. Is this clear? That's why flow in the bifurcated and bended tube is turbulent. So there are the three reasons that the flow in aorta is turbulent. The high speed of the flow in the aorta, the bended aorta, and short aorta. Is this clear?
Can you repeat the three reasons?
There high speed of flow in the aorta, bended aorta, and short aorta that it can develop laminar flow.
Okay, Diak, Matuka.
Yes. When we have to measure the pulse, which kind vessel we have to find? Bifurcated. Because in the bifurcated place, there will be the turbulent flow. Is this clear?
Diak.
Can you repeat, please?
Pulse, when you calculate the pulse, what you have to find? The bifurcated vessel. Is this clear?
Yes.
Yes. No, also we discussed this on the previous lecture that which vessel have the monolayer and do not need the multi-layers, the capillaries. Why? Because the Laplace pressure directed in the center, where is more, in the capillaries, narrow capillaries, or in the wide aorta? In the narrow capillaries, because Laplace pressure is inversely proportional to the radius of the vessel. And we have, you can see here, we have to discuss, so this is the systolic and diastolic pressure, or the systolic pressure is a pressure by which the heart excludes the blood out of the ventricle into the aorta, yes. Diastolic pressure is the pressure, why the diastolic pressure into the heart is less as in the aorta. Do you know? Due to the resistance of the aorta. Aorta cannot be widened to the size of the ventricle. Is this clear? That's why the diastolic pressure in the aorta is 80, where in the ventricle it will be fall down less as 20. The difference between the systolic and diastolic pressure is known as the pulse pressure. If the normal systolic pressure is 120 and diastolic is 80, the pulse pressure is equal, what is mean
40.
of the pulse pressure?
40.
40. It is normal pulse pressure. For example, your patient has pressure 120, 100. What is the pulse pressure?
20.
20. What diagnosis you will put?
Low pressure.
No. It is that aorta is too resistant. Aorta is too resistant. It cannot be. Listen to me. Aorta is too.
Mute your mic, Desumba.
Please close. No, close your microphone. Listen to me.
I'll be like, I can't find my key. Then you come.
Can I continue the lecture? Can I continue?
Can you just mute your mic?
Please close microphone.
Professor, you can mute them.
Just mute your mic, Professor.
Oh, I forgot to put the
Listen to me. I cannot speak so.
What?
Dawson, close microphone.
Yeah,
Without what?
okay, I got 2 out of 3 because of that.
Oh, that.
So, it is too high resistance of the aorta. It cannot divide it. That's why diastolic pressure increases and pulse pressure decreases. But if the patient has the systolic 120, but systolic 40 or 60, what means this?
Pulse pressure is high.
Pass by, because aorta is too wide. Now this
Yeah.
may be when you are pushing the bulbs many times, it will be increased in the volume. The sportsmen or workers who are making the very hard work, very hard exercise, they usually have the very intensive blood output, and their aorta will be continuously widened. After, with the aging, the wide aorta will support the decrease in the diastolic pressure, the increase in the pulse pressure. As a result, the medium pressure of the blood will be decreased, and it will be not enough supply of the blood flow to the patient's body. Is this clear?
Doctor, can you repeat?
When the pulse pressure increases, it is related with the too low resistance of aorta, related with the hard exercise in the case sportsmen or workers. Is this clear? my dears, this you have to study who attends and who do not attend. Everybody has to study this material for the next week. Next week, I will explain you the breathing. And after the holiday, from 10 January, you will have continuous studying and you will have the oral and written test on the whole fluid mechanics. Is this clear?
Yeah.
Yes. Goodbye.
Akvamis. Dili madloba.
Thank you, Miss.